My pleasure to welcome Eriko Hironaka, and she's going to talk about Alexander-Teichmueller polynomials for graph maps and replication to out of FN and mod CGN. FGN, sorry.
So I'd like to thank the organizers for the invitation and for the introduction. So what I'm going to talk about is actually kind of a new or a simple way to compute the Alexander polynomials that comes from ways to compute the Teichmueller polynomial. So in the it was very nice to have the previous talk just before mine, because first it motivated these polynomials, but also there was a nice comment that the Alexander polynomials are easy to compute compared to the Teichmueller polynomials. But actually what I find interesting about the Alexander polynomial, it has many, many applications, and there are many, many ways of computing the Alexander polynomial that people use. And this is probably a different one. And so it just, there are reasons to, it's a good thing to point out that there are reasons to compute the Alexander polynomial this way, because it specifically compares the Alexander polynomial and the Teichmueller polynomial. So a lot of people know lots of different ways of computing the Alexander polynomial, so this may be different. Okay, so what I'm going to do is explain this first in terms of graph maps, and then see how it applies to out FN and mapping class groups. Okay, so what's a graph map? First, let me just say what I mean by a graph. So this is just a simple, it's a finite graph. So it has a finite set of vertices and edges. And a graph map, you can also think of this as a one complex. So it's a topological space. And a graph map is just, you can think of it as a continuous map on the pairs. So vertices have to map to vertices, and it has to be continuous. So edges will map to edge paths. And we usually think of this mod isotopy rel the vertices. Okay, so it's a combinatorial thing, basically. So how does this, there are different ways of doing this, organizing this talk. One was to just completely go through with graph maps, but I've decided to sprinkle in, okay, how can you picture this in the other context? So if you have an automorphism, you can take, of the free group, you can take a representative automorphism, and this can, in some cases, be nicely represented by a map from a bouquet of circles or any one complex that happens to have the same fundamental group as Fn. So I guess you can always do it this way, so that if this is an automorphism, this is a homotopy equivalence. And so this is the kind of graph map that I'm thinking about. Okay. And for a mapping class from a surface to itself, again, you can try to take some kind of nice graph sitting inside the surface that fills the surface, like so by filling the surface, I mean that this is again a one complex sitting inside there, and the complementary components are either disks or punctured disks, once punctured disks. So you can have a map between here that's given by taking gamma, looking at its image under phi inside SGN, and then kind of retracting up to gamma. Okay, so this is sort of the picture that we're thinking of. These are they're not canonically associated to phi. They sort of, you can try to find such models for these automorphisms. Okay, so given the graph map, we have two associated maps, homomorphisms. So F-alg and F-geo. And from RE to RE. So you can think of this as maybe real labels on the edges, or maps from the edges to R, or just the R to the number of edges. Okay, and these are defined as follows. For every edge, f of e, as I said, is a path of edges, possibly with orientations reversed. So let's assume that there's just some fixed orientation on the edges. So then the algebraic map is just, we'll send fe to s1 ei1 plus sk eik, and the geometric one just sends it to the positive sum. Okay, so here you can see already that there can be cancellations, whereas here you're counting everything. So let me just give you a pictorial example. So this is something which actually doesn't come from either of those situations, but here's a graph. Let's label this edge A and this edge B. And these are the three vertices. And we can map this like this. Okay, I'll try to make this maybe bigger. Okay, so this is A, and this is B, let's say, the image of A and the image of B. And they're not really, there's no sort of ambient surface going on, but this is just to sort of show where everything goes. So the F-alg would be the linear map given by the matrix. So A goes to this, but these cancel because they're the same edge, one going one way, one going the other. So it would be -1. Sorry, I'm assuming these orientations here. So it would be -1, 0, and B would be -1, and then 1, -1, 1 on the B side. So it would be -1, 1, like that. Whereas F-geo would be, you just count, so this A would go 1, 2, and B is 1, 3. Okay, and this tells you something. There's a reason for the algebraic and geometric. I mean, so this tells you the something which, so let me just, so if you look at the largest eigenvalue of this, or the spectral radius of this, you get f alg is 1. This is actually periodic. And this one, the largest eigenvalue is 2 plus square root of 3. And what that's telling you is that if you take a vector and you keep applying f, then the size of the vector is just going to cycle around because it's periodic, and so it doesn't increase the size. Whereas this one, when you apply a vector, in norm, it's going to grow, and the growth rate is 2 plus square root of 3. So this is sort of the geometric growth, and this is the algebraic growth. Okay, so for applications to the out fn and mapping class groups, if phi is in out fn, and you might notice, for those of you who study these things, I didn't really specify what kind of graph map this is. These are not necessarily train tracks, okay, which I'll explain later. But you always get that f alg is is sort of the growth rate for the map phi star acting on the abelianization, which is just Zn. And but FGO will just give you a upper bound for the growth rate of word lengths. So phi star acting on, so I should say, the growth rate of phi to the n, the length of phi to the n of a word to the 1 over n. Okay? And for phi in the mapping class group, so phi is going to give you a map from H1 of S to itself. So f alg is just the homological dilatation of phi. Again, so I just take a graph which fills the surface, and FGO is sort of an upper bound for the entropy of phi. Okay, but you can do better in special cases. So, for example, so in particular, if phi in out fn is fully irreducible and atoroidal, then there exists a graph map so that this is going to be exactly the growth rate of word lengths. And if phi in mod SGN is pseudo-Nosov, then there exists a train track map. So it's even better. There is a graph, which I'll call tau, where at the junctures, we can take tau to be trivalent, and at the junctures there's smoothings, and eventually any simple closed curve on SGN is going to be carried on the train track after iterations by f. Carried means that you can, during the retraction, when you retract the images to in SGN to the train track, it's going to fall smoothly on the train track. Yes?
How do you define the growth rate of the word length? Do you take the supremum over all W? Or,
Oh yeah, right. Or if you just chose a W, it's a bigger than or equal to. So. Oh yeah, but yeah, in this case, right. It's the I guess it's the lim sup. Supremum, yeah. Over.
In this case, it doesn't matter which W.
No.
If it's a
That's what. Yeah. Okay.
It doesn't matter.
Yeah. In the fully irreducible case, it doesn't matter. Right.
No,
So it's like
Take the three over.
the fully reducible and a
and atoroidal.
If it's toroidal, then you may have a fixed.
Sorry. Yeah.
Yeah, it is.
Right.
In this case,
Yeah.
it
So this
doesn't
is
matter.
kind of removing all the bad things that could happen in locally. But yeah. So if you take omega non-trivial, then the growth rate will be equal to. Okay. And in the pseudo-Nosov case, it's the same thing, that FGO is the geometric dilatation of phi. So take any curve, it's eventually carried on the train track, and the growth rate is going to be the growth rate of the train track, and it's going to be the largest eigenvalue of that thing. Okay, so what I'm going to do is show how to find these. Oops, I think I just erased them. But I'll show how to find these matrices using this trick, and then use that to find the Teichmueller polynomial and Alexander polynomial. So maybe I should mention where this is going. So if you have a element of out Fn or of mod SGN, that's pseudo-Nosov, let's say. So this is the fully irreducible atoroidal case, and this is the pseudo-Nosov case. Then these come in natural families. So Dowdle-Kapovich and Leininger showed that there's actually, in some sense, a whole family of these things which have related dynamics, and I'll explain that further. And it's related to the Thurston norm, etc. So there's sort of a family of these things that are organized in a really nice way. And here also there's this fibered face theory of Thurston, Fried, and McMullen, where you can organize the pseudo-Nosov mapping classes. Changing the surfaces can change, but if you're focusing on a certain dynamical system, there is a family where the dynamics is sort of preserved and organized in a nice way where you can compute things. Okay, so what we're aiming for is that if you have graph map, there's sort of an analogous thing. And because graph maps are, as you'll see, they have these nice sort of properties because they're sort of just graph maps, they can find, doing this part of the story can help you to find the invariants over here. So over here you have Alexander Teichmueller polynomials, but we'll show how you can do it this way and then what it translates to in the other direction. So there's a key idea from graph theory. that goes as follows. So if, let's say A is a non-negative integer matrix, and A to the n is completely positive for all n bigger than or equal to some number, then we say A is parent Frobenius. And it has the property that this largest eigenvalue, which I'm denoting that way, is a Perron number, which means that if you look at that number, it's a simple eigenvalue. None of its conjugates are eigenvalues, and so all the other eigenvalues lie strictly inside the circle defined by lambda. So this is here. Okay, and there is a positive eigenvector for this Perron number eigenvalue, and so they're really nice types of matrices. And associated to a Perron-Frobenius matrix, or any non-negative matrix, you can find a directed graph D, so where the vertices are the entry, the number, this is a square matrix. So that are the rows or columns, and the edges, you have an edge for each or you have n edges, let's say k edges, if between vi and vj, if aij equals k. So you have no edge if the entry is 0. Okay, so I really meant to keep that picture, but I'll write it over here. So here's my graph, and let's see, this is A and this is B, and let's see if I can do this again. I think I did it the wrong way. Okay, so in this case, this is A and this is B. The directed graph, well, so the matrix was 1, 2, 1, 3. And the directed graph is going to have 2 vertices, and this is going to correspond to A, and this is going to correspond to B. So there's an edge from B to A, and there's an edge from A to itself for this row. And there are 2 edges going this way from A to B, and then 3 going this way for B. Okay, and then so this is the directed graph. And now I'm going to show you how to go from the directed graph to the characteristic polynomial of this thing. So being 2 by 2, it's not hard. It's just x squared, the determinant is 1. The trace is 4, so x squared minus 4x plus 1. So there's another way to get that polynomial, which is you make a 1 complex, which is actually the, or actually it's a It could be in general an n complex, but it's the analog of the curve complex for surfaces. It's just you take the so this is the union over k of sigma k, where sigma k is the k tuples of disjoint directed cycles. Okay, so in this case, sigma so there's a cycle, these are two cycles, there's a cycle like this, right? So we have one cycle that goes around here, 3 cycles going around B, and then there are 2 cycles this way. And then these are disjoint, so we have lines like this, and that's it. Okay, so that's the 2 complex associated to this graph. Sorry, 1 complex in this case associated to this graph. And now I compute a polynomial, call it theta, which is just given by, in general, it's given by sigma in here. So every simplex in here minus 1 to the dimension of sigma plus 1 times x to the number of vertices in sigma. Okay, so this is, in this case, in the example, what do we have? We have, so there's 1 for the empty complex. There's 1, 2, 3, 4, 5, 6. But this one has 2, these ones have 2 vertices, and these all have 1 vertex. So you have 4 of these with just 1. That gives you 4x to the minus 1. This should be a minus. And then minus 2x to the minus 2 for these 2. And then plus the one-dimensional ones. So this has 2 vertices involved, because each of these has 1. So that's x. That gives you a contribution of x to the minus 2, and there are 3 of them, so you have this, which gives you 1 minus 4x inverse minus x to the minus 2, and that's equivalent to this up to as a Laurent polynomial, okay, up to units. Okay, so this gives you a polynomial for, and this is a general fact, that if you have a non-negative matrix, you can get the characteristic polynomial this way. And then you could also do this. So this is just a little variation. If you want to look at the algebraic map, you just have to put, all you do is you put signs on these, because all that's happening is that you're keeping track of the orientations of these arrows. So these arrows are either orientation preserving or reversing. So this is, so going toward A, this should be minus and minus, because A was directed this way and we're going in the negative direction. For B, it goes plus and then minus. And here it's plus, minus, and plus, because you have plus, minus, and then plus. Okay, so you can do the same thing, but now you take your complex and you label these vertices according to the sign of the cycle. So this cycle, these cycles have, it's easy to see what their sign should be. With this one, it's a minus and then a plus, but totally it's doing a reverse, right? So this is going to be, one of them is going to be minus, and the other one minus minus cancels, and so you get that. And then you do the same thing. So so narrow, this is like the baby Alexander polynomial, is going to be sigma minus 1 to the dimension of sigma plus 1. The sign of sigma x to the minus sigma. And if you do that, you'll see that you get x squared minus 1. So I don't know how I'm doing for... So yeah, why not do that? So again, what you do is you have 1 minus, and then you have 2 pluses and 2 minuses, so they cancel, right? And then here, they also cancel, and so there are no x inverse terms, so x inverse times 0, plus x to the minus 2, so this one is a negative, positive, and negative, so in total you get a negative x to the minus 2. So 1 minus x to the minus 2. Okay? Okay, so now we're going to do the thing. We're going to go from one example of a mapping class or graph map or an automorphism and expand it to a whole family of examples. But I'm going to do it not using the geometry of the situation, like out f n, etc., but rather using the combinatorics. Okay, so first of all, when you have a graph map, then you can make a mapping torus. So which we've seen a few times so far. So this gives you an object, which is some kind of complex. This is gamma, this is 0, 1. Okay, and then there's a sort of trivial flow going on, but then it's glued together by the map F. Okay, so let's call this XF. And D, the digraph associated to F, the directed graph associated to F, and I'm going to take the geometric version. I mean, just forget about the labels for a moment. This maps, not necessarily injectively, but it maps to gamma, kind of naturally. So, for example, if you have, in our example, now our example is a little weird because it already looks like everything has to cancel, right? You have B going back and forth. But let's not worry about that for a second. I'm just trying to make a simple example. So then, if A is oriented that way, B is oriented that way, what's happening is you're just sort of saying, okay, this is A inverse, B, B inverse. Here is A inverse going this way. B, B inverse, B. And if you put a vertex here and just draw all these lines, you're going to get an image of D inside the mapping torus. Okay, so what this gives you is a map from the cycles to whatever you like. So H1 of XF with coefficients in Z. And so now we can add to our labels. And for each of the cycles here, we can give a group element, an element of H. Okay, so so we can add to let D sort of more decorated be D with, sorry, I meant sigma. Be sigma with the additional labels sigma, so H of sigma on each sigma. Okay, I mean, for example, just we can label the vertices. Okay, and so that's what's going to give you our Teichmueller polynomial and our Alexander polynomial. So the Teichmueller polynomial is going to be sigma minus 1 to the dimension plus 1. Now x to the, or if you want to think of it as h of sigma inverse. And the Alexander polynomial is this thing h to the, sorry, with the sign h to the h of sigma inverse. Okay, and now these are elements of the group ring. Okay. So I've sort of said what the invariant is before telling you what it's an invariant of. So let me go back to the application. So if f gamma to gamma is a graph map, and phi is f star, thought of as an element of Fn, where Fn is pi 1 of gamma, okay, then that polynomial that you get from going through all that thing is equal to the Alexander polynomial for where G is the phi bicyclic group for phi. Now if, in addition, if phi came from a fully irreducible, if phi was fully irreducible a toroidal, then this theta is going to give you what's called the McMullen polynomial or Teichmueller polynomial, defined by Dowdle, Kapovich, Leininger, and Algom-Kfir, me, and Rafi independently. This definition is more along the lines that we presented it in the paper. And there may be some discrepancy, but it would be by a factor that is sort of cyclotomic. So up to cyclotomic polynomial factors, these are the same thing. Okay, so you can get the polynomial in this way. If phi, actually, are there any questions? So if phi is a pseudo-Nassau map, then delta is the Alexander polynomial for M, where M is the mapping torus. So and well, actually, so I didn't need the pseudo-Nassau for this. And then for the pseudo-Nassau, if you have theta is the Teichmueller polynomial, defined by McMullen. Okay, and so what do these do? So you can see already that they look a lot like the little thetas and deltas. So I'm just going to use theorems proved by other people since I only have 5. I mean, that you'll have to look up to see in more detail. But I talked about the families of these objects. So in work of Dowdle, Leininger, and so they look at they define a cone sitting inside the homomorphism of G. So G again is this free bicyclic group. We're assuming that C is fully irreducible and atoroidal. Then they define a cone in here, which contains the natural map, this natural map from G to Z coming from that decomposition, so that for all integral alpha in AF, there exists a train track map F sub alpha, gamma sub alpha to itself, such that F alpha lower star on the corresponding free groups is fully irreducible atoroidal. And then in this cone, and this is a nice polygonal, convex polygonal cone, polyhedral cone. In this cone, if you specialize the polynomial by alpha, so you think of these as elements of ZH. So alpha, since alpha is a map from H, which is, in this case is the violinization of G, this will give you a polynomial, and the largest root of that polynomial is the growth rate of words by the action of F. Okay, so, I mean, in particular, the one you start with, theta, is a specialization of the bigger theta, and similarly for the deltas. So this is the sort of geometric dilatation, the growth rate of the word length, and if you want, there's a one-dimensional Alexander, there's an Alexander polynomial in one variable associated to any map to Z as well, and that's what this is too. Okay, so you can get these things back, and also Dowdle, Leininger I should say this part is also starting with the existence of this cone. This was proved independently by us. And they also showed that if you take, and luckily in the last talk, the norms associated to group ring elements was defined. So this has a face, a top dimensional, so the norm ball for this norm has a top dimensional face whose cone is the BNS cone containing AF. So AF, if you remember from the last talk, would naturally, because it corresponds to a decomposition, lie completely inside the BNS. There's a bigger BNS cone component which contains it, and they show that if you look at this norm ball, you'll get that cone. Okay, so this being able to compute this thing is nice because you have also the extra information about the whole group. And remember that all these computations are just coming from one single element of the family. If you chose a different element of the family, you'd get the same cone, etc. Okay, and finally, in the mapping class group case, the Teichmueller cone is actually equal to the Teichmueller norm is equal to the Thurston norm. No, I shouldn't say that. Sorry. So the cone define. What do I want to say? The fibered cone containing the fibration with so M is the mapping torus. You have a fibration to S1 with monodromy C S to S. So we started with this mapping class, and we made the mapping torus, which has fibration. H is going to be the first homology of M with coefficients in Z. And so theta is in CH, and so is delta. So again, delta is the Alexander polynomial. So theta defines a norm on H homomorphisms from H to R, and one of the cones defined by a top dimensional face is the fibered cone containing phi. So the fibered cone containing phi is one of the cones defined by theta. Okay, so what would be nice is to actually get at the Thurston norm. But what we have is, so that by the theorem that was mentioned in the last talk, on a fibered cone, the Alexander norm is equal to the Thurston norm. So this is McMullen. And I'll just leave with one general sort of remark. For general graph maps, we have the inequality mentioned also in the last talk. And that follows very easily from just the presentations of the the two polynomials side by side.
That's a theta instead of c.
I'm sorry, yes, thank you. Yeah. So I'll stop there.
Thank you very much for a very interesting talk. Are there any questions, comments? Okay. Let's thank Eriko again.